Hello, ladies and gentlemen. Today we're going to take a look at segments themselves and this new idea or new understanding of congruence. And so you may have heard that word before. I'm hoping you have. And we're going to take another look at that and remind yourself what it means to be congruent. So our learning today is going to focus on just using those basic segment properties to solve problems. So we're going to take a look at a couple new ideas, write them into our notes, and then apply them in terms of solving problems that deal with segments. So this part I need to make sure that you have into your notes. There are some different types of geometry statements that you're going to hear about this year. The first one is called a postulate. Now, rather than just say we know this fact or this thing, in geometry, the facts or the statements or the ideas that are presented are pretty formal. And because they place names to them or they call them certain things. And one of the things that we're going to refer to today is something called a postulate, or sometimes it's referred to as an axiom. Basically, this means it's sort of like a definition in a way. It's a statement that's accepted without proof. So nobody really had to prove it. It just became sort of this accepted idea or this basic understanding that people had. Again, it was something that is pretty common sense, if you will. So people didn't really need to be shown or have it proven to them that it really works or that it's true. Whereas other types of statements we're going to come across this year are theorems. And just like the word kind of implies, theory, those things do need to be proven. Just having a theory is one thing, but when you can prove it now, it becomes a theorem. So in geometry, we're talking about theorems as well as postulates. So we're going to talk about a special postulate today, and I need you to get this one into your notes. It's called the ruler postulate. The ruler postulate is kind of a funny name for a basic idea that says the distance between 2 points on a line is the absolute value of the difference of the coordinates of the 2 points. So that's a fancy way of saying basically that you can find the distance between these 2 points, A and B here, if you just measured or you thought about those coordinates or you put them on a number line and you found the difference or you subtracted those two values. Now the absolute value is in there, of course, because we can't have a negative distance. We always want to make sure that that's a positive distance. They call it the ruler postulate because this is sort of what we do with rulers anytime we use them, okay? So imagine here a ruler comes in like this, and I'm placing that ruler just there. Do you know how far it is or what the distance is from A to B? Can you say what the distance or the length segment AB would have there? Well, notice I didn't put the ruler over at 0, but you see a 2 above the A and an 8 above the B. If I were just to subtract those two, 8 minus 2 makes 6. So the distance here is 6 inches in this case. So it's basically using a ruler is what this ruler postulate is saying. Now I wouldn't have had to place the ruler that way. I could have placed it further along this way. Again, same idea. One of them's at 5, the other one's at 11. I just subtract to get the difference here. That's still 6, right? It's 6 units long, no matter where I place this ruler. It's this idea that you can think about rulers just like you think about number lines. So what else can we do with segments? You don't need to write this part into your notes, but you've done this before. Let's say that we're traveling from Dickinson all the way over to Fargo in North Dakota here. And Dickinson to Bismarck, the sign says, is 99 miles. Bismarck to Fargo is 189 miles. So how far should the sign say for Dickinson to Fargo? Well, you're probably thinking, wouldn't I just add those two? Right, you could do this sort of intuitively, but we're talking about adding segments here, aren't we? Dickinson to Bismarck is a segment, Bismarck to Fargo is a segment. So another postulate that was said or told to people at the beginning of geometry studies is the segment addition postulate. Segment addition postulate simply says that we can add segments together, and I would draw this picture in your notes. Notice it says if B is between A and C, just like Bismarck was between Dickinson and Fargo, notice it says between and not in the middle or the midpoint. It just has to be somewhere in between. Then I can add segments together. AB plus BC will be the distance from A to C. So it's sort of intuitive. You kind of already understand this. That's why it's a postulate. Nobody had to prove it to anybody. They're like, yeah, we kind of get this. It makes sense. Segment addition tells us that we can certainly go ahead and add segments or think about segments being added together and use numbers then to calculate missing lengths. So what happens when those segments have the same length? This is where that word congruent comes in. Congruent segments. Two segments are congruent if they have the same length. Notice here, I have a segment AB, that's A to B, and a segment CD. And both of them have a length or are labeled with a 12. Because they're both labeled with a 12, we call them congruent. We say that they are congruent segments because they have the same length. I can mark that congruency on the picture here with this little dash right here. That's marked with one dash. This is marked with one dash. Because they're both marked with the same one dash, that means that those two segments are congruent. So even if the 12 wasn't there, I would still know that they're meant to be the same length. Underneath there, make sure that you get this part in your notes too. AB, notice segment, AB is congruent to CD. In symbolic notation, we typically write it like this underneath. Notice it's still segment AB, but instead of writing the words is congruent to, there's a symbol. There's the equal sign, meaning equal length, but a little squiggle above it because we're not talking about equal segments, we're talking about equal lengths. So segment AB is congruent to segment CD there. So that might be new to you. I'm not sure of your background experience if you've seen that congruent symbol before, but that's something we're going to use quite often this year. So let's go ahead and draw this example in your notes. We're going to do 3 examples here. So you have the basic idea. We can measure segments using numbers, and we can also add them together using segment addition. Those are our 2 big postulates. Now let's draw this diagram in your notes. It says, here's this segment up here. We have M, P, Q, and N. And it says, explain what MN means and what MN means. Now you're thinking, aren't those 2 the same thing? Key idea up here, ladies and gentlemen. Check this out. That's segment. And we need to talk about what does it mean when there isn't the segment bar above it. So let's write this part into your notes. We need to make sure that we have that clear as the difference between those 2 pieces. Now here's what they mean. MN with a little line segment above it is the line segment itself. So MN is referring to that line segment itself because it has a little line segment picture above it. Whereas the one without it means the length of line segment MN. So MN without the little dash above it means that we're asking for an actual length of that segment. So now let's do a couple a couple examples here using this picture. PQ, it says if PQ equals 4, so if I were to place a 4 right up here on my picture, and QN is 5, then what is PN? Well, look at that picture up there. If QN is 5 and PQ is 4, wouldn't we just add those together? Doesn't that make sense? Yeah, because we know that PN, that whole segment, is one little segment plus another little segment added together. So we'd add those 2 together and we get 9 for the whole segment. Now what if MP is 3 and MN is 14? Then how far is it from PN? So if we switch this up a little bit and I scribble these out here, these are not here. If MP is 3 and MN all the way across here is 14, then how far is it? Notice it's a distance because it doesn't have the little segment bar above it. We want the distance from P to N. Well, you're not going to really add segments here, but you're going to think about the 2 segments that are in this picture adding up to make the bigger segment. So MP plus PN is equal to MN all the way across. So basically for this picture we would take and subtract instead of add. There isn't a segment subtraction property. Segment addition can be undone basically, and you know your inverse operation, so sometimes you might have to subtract to find out that PN is going to be a length of 14 or a length of 11. Okay, let's look at one where you don't have a picture. We're going to practice drawing some pictures here. Example 2. There are 5 collinear points, P, Q, R, S, and T, in that order. So the first thing I would do is draw myself a line here, doing the best I can here, and I'm going to place those on here. This might be P, oops, sorry. This would be P, then I need Q, then I need R, then I need S, and then I need T. Now I don't know how far apart each of these was supposed to be from each other, but that's okay. I'm just going to go by the fact that there are 5 collinear points. That means they're all on the same line. PT in my picture, from here all the way to here, it says is 20. So I'll draw that. Q to S, here to here, it says is 6. And then it says PQ equals QR equals RS. That means the length of PQ, RQ, and RS are all the same. In other words, those 3 segments are congruent. So I'm going to go ahead and put little slashes on here. PQ is congruent to QR then and RS because they all have the same length. Now, when I put those little slashes on there, it didn't really give me another number to write, but I know that I have a 6 up here. These two together make 6, which means this piece has to be 3 because it's equal to this piece. And 3 plus 3 makes 6. Now, the other piece marked with a little slash there has to be 3 as well. And so far, out of my whole segment from P to T, I've used up 3, 3, 3. That's 9. That means S to T, the only other piece I don't have labeled, has to be 11 to make that 20 total. So if that's the case, guys, and we have this beautiful picture, could we find all these missing pieces? Sure. All we have to do is use our diagram to the best, or draw a good diagram, use our diagram here to fill in other missing pieces that we don't know. So how far is it from P to Q now? We could say, well, it's 3. I can see it clearly from my picture. How far is it from S to T? It's 11. I have that marked in my picture. How far is it from R to P? Now, it doesn't matter that we're going to the left here. R to P is still just going to be 6. 3 plus 3 more. R to T, how far is that? R over to T. Well, that's 3 and 11 more, 14. What about S to P? S all the way over to P, that's 9. Everything but that 11 on the end, right? And then Q to T, careful now, Q to T all the way over, that would be 17 if you added all those numbers. So we can find anything, let me go back, using a good diagram. So if you don't have a good diagram, make sure you draw one. Listen to those descriptions given to you in words, or if they're given orally by somebody else, listen to the description and then draw that good picture and you'll be able to find any missing segment you need. Now our last example we want to get into our notes involves a little bit of algebra here. And again, it doesn't have a diagram or picture, but we're going to go ahead and draw one. It says, suppose M is between L and N. Use segment addition to solve for the variable x. Then find the lengths of segment LM, segment MN, and segment LN. So let's go ahead and draw a good picture here of this situation. It says suppose M is between L and N. So up here, I'm going to place 3 points here. Oops, sorry. 3 points. And I'm going to place M in between L and N. It says use segment addition to solve for the variable x. Well, I don't have anything labeled up here until I look down in this area, and here's my description. It says LM is 5x plus 8. I'm going to label that. MN is 7x minus 4. And LN, that's the whole piece here, is 40. Now you might be thinking, well, if the whole piece is 40, isn't each piece 20? Not necessarily. It said M is between L and N. It didn't say M is in the middle. You can be between two things and not be evenly spaced. So with that in mind, we can't just assume each little piece is 20. But we do know that the little segment LM and the little segment MN add together to make a total of 40. So what I would do is use my algebra skills here to add those little segments. We would know that LM plus MN equals 40. So LM plus MN equals that whole piece, which is LN, right? And LN happens to be 40. So now all we have to do is substitute this algebra stuff here, these expressions, in up here and here, and we have something that we can solve. So 5x plus 8 plus 7x minus 4 equals 40. And now remember from algebra, you combine like terms, you get 12x, and now 8 plus negative 4 is positive 4, so you'd have 12x plus 4 equals 40. And then we'll subtract the 4, so 12x equals 36, so x would be 3. So I know what that value of x is. Let's go back to the directions. It says solve for the variable x, then find the lengths of all three pieces. Well, we already know ln is 40, but how long would lm be if x was 3? Well, back up here where this x is right here, we're going to place a 3. 5 times 3 is 15, plus 8 makes 23. Then let's go to mn. mn, if I were to place the 3 in here, where the x is, 7 times 3 is 21, minus 4 makes 17. And then my last piece, ln, was given to me as being 40, so I don't have to actually do any calculations here. But let's double check. Does lm plus mn make the longest segment ln? Yeah, 23 plus 17 does make 40, so we did it right. So we can use segment addition and understanding that segments have length to help us solve segment-related problems. I want to thank you again for taking good notes today, and I'll see you later.